So next, I want to discuss a very important concept, which is the concept of the complete basis of eigenstates. So in previous lectures, you saw that suppose we had a solution to the time-independent Schrodinger equation. So the solution was something like this. Some state has some energy, EI. So this was an eigenstate of the Hamiltonian operator. And then, if you could solve the time-independent Schrodinger equation, then the time-dependent solution with energy EI would just be given by the time-independent solution times an exponential factor of this form. So this is actually a very, very useful result. It allows us, in conjunction with the idea of a complete basis of eigenstates, to find out the time evolution of any arbitrary state. Okay, so now recall that the energy operator, the Hamiltonian operator H bar, is a self-adjoint or Hermitian operator. Now, it's a theorem in quantum mechanics, which we will not prove in this course. And the theorem is that the complete set of eigenfunctions of a physical observable represented by a Hermitian or self-adjoint operator form a complete basis for all wave functions of that system. So what does this mean? Suppose that you have some state, some arbitrary state, which is a function of space and time. And let's just take a particular time. Say we call psi of x to be the wave function at time t equals to 0. Then it says that this wave function at a fixed time can be expressed as a linear combination of all the eigenstates of a physically observable operator such as the Hamiltonian. So if we take all the eigenstates of the Hamiltonian operator, which is psi I of x, so these are essentially the solutions to this equation, then we can write psi of phi of x to be a linear combination of all the energy eigenstates. In principle, there will be an infinite number of those things. So we write it as Ci psi I x. So this is a very, very powerful result. So the space of all the wave functions of a quantum system, along with the inner product that we defined in a previous lecture, is called a Hilbert space. And it's named after David Hilbert, who first formalized the mathematical properties of such spaces. So let us write that down. So what is a Hilbert space? So it's the space of all the wave functions of a quantum system with an inner product of course an inner product has to be a convergent quantity defined on it. And the theorem that we just discussed here is saying that the complete basis of wave functions, they form a basis for Hilbert space. So that means that if we solve the time-independent Schrodinger equation, we have a complete basis of the Hilbert space.